Let us consider measuring the length of a pencil, denoted as L. To do this, we read the values of x1 and x2, which are values corresponding to the markings on a meter rule. Let's say the values are 2.0 cm and 22.4 cm, and the uncertainty in each reading is 0.1 cm. So we can write delta x1 equals to 0.1 cm and delta x2 equals to 0.1 cm. As you can notice, the uncertainties are to one significant figure. This is a rule of thumb. The uncertainty should always be to one significant figure. So we can write L equals to x2 minus x1 equals to 20.4 cm. Since there are uncertainties in x1 and x2, therefore there will be an uncertainty in L. This is what we mean by the propagation of uncertainties. The uncertainty in L is denoted as delta L and is calculated as delta L equals to delta x2 plus delta x1. Pay attention to the fact that uncertainties are always added and never subtracted. This means uncertainties always accumulate. Hence we get delta L equals to 0.1 cm plus 0.1 cm equals to 0.2 cm. And finally we write the length of the pencil L equals to 20.4 plus or minus 0.2 cm. The number of decimal places in the uncertainty must match the number of decimal places in the quantity. So here the uncertainty is to 1 dp and the quantity length here is written to 1 dp so that it matches with the number of dp's in the uncertainty. Now the quantity delta L over L is called the fractional uncertainty, is equal to 0.2 divided by 20.4, which is equals to 9.8 times 10 to the power of minus 3. And if we write the value of delta L over L as a percentage, which here is going to be 0.98%, then we call it the percentage uncertainty. Now let us consider another situation. Let us say I have a liquid of volume V1 equals to 20 plus or minus 1 centimeter cube. And let's say we add a volume V2 of another liquid. V2 equals to 18 plus or minus 1 centimeter cube. Then the total volume V is equal to V1 plus V2 equals to 38 centimeter cube. The uncertainty in V is delta V equals to delta V1 plus delta V2, where delta V1 is equal to 1 centimeter cube, delta V2 is equal to 1 centimeter cube, and therefore delta V is equal to 1 centimeter cube plus 1 centimeter cube equals to 2 centimeter cube. So we can write V equals to 38 plus or minus 2 centimeter cube. Since the uncertainty is to the nearest centimeter cube when returned to 1SF, the value of the volume should also be to the nearest centimeter cube so that it matches with the uncertainty. Now let us consider another example where we have an ammeter measuring a current I equals to 4.3 plus or minus 0.2 ampere, and the duration of this current is T equals to 2.34 plus or minus 0.02 second. Let's say we want to get the amount of charge Q that passed through the ammeter together with its uncertainty. So we use Q equals to IT, and if we substitute the values of I and T, we will have Q equals to 4.3 times 2.34 Coulomb equals to 10.602 Coulomb. To get the uncertainty denoted as delta Q, we use delta Q over Q equals to delta I over I plus delta T over T, where delta I over I is equal to 0.2 over 4.3 and delta T over T is equal to 0.02 over 2.34. And if we substitute, we have delta Q over Q equals to 0.2 over 4.3 plus 0.02 over 2.34. Then we get delta Q as 0.2 over 4.3 plus 0.02 over 2.34 times Q. And if we substitute the value of Q, we will have delta Q as 0.554 Coulomb. Then we write delta Q to one significant figure, and we will have it as delta Q equals to 0.6 Coulomb, and therefore we have Q equals to 10.602 plus or minus 0.6 Coulomb. And now we have to write the value of Q to the same number of decimal place as the uncertainty. And if we do this, we will have Q equals to 10.6 plus or minus 0.6 Coulomb. Let us consider another example where we have the kinetic energy of a car given as Ek equals to half mv squared, where m is the mass in kilogram and v is the speed in meter per second. M is equal to 1000 plus or minus 10 kilogram and V is equal to 15.0 plus or minus 0.1 meter per second. Let's say we need to find the uncertainty in the kinetic energy Ek. So we find it like this: delta Ek over Ek equals to delta M over M plus 2 times delta V over V. And if we substitute the values, we will have 10 over 1000 plus 2 times 0.1 over 15.0, which should give you 7 over 300. And therefore, delta Ek is equal to 7 over 300 times Ek. And if we substitute the value of M and V, then we have Ek as half times 1000 times 15.0 squared equals to 112,500 joule, and delta Ek is equal to 2625 joule, which is equal to 3000 joule to one significant figure. So here we have our Ek equals to 112,500 plus or minus 3000 joule. So here the uncertainty is to 1 SF and is therefore to the nearest 1000. So the value of the Ek should also be returned to the nearest 1000. And if we do this, then we get the Ek equals to 113,000 plus or minus 3000 joule. As a final example, let's take a situation where we have a voltmeter connected across a resistor with resistance R, and there is an ammeter connected to measure the current passing through the resistor. Let's say the current I is equal to 2.5 ampere plus or minus 8%. And the voltmeter reading is V equals to 24.2 plus or minus 0.2 volt. And let's say we need to find the uncertainty in R. So we are going to use the equation R equals to V over I. To find the uncertainty in R, so we write delta R over R equals to delta V over V plus delta I over I equals to 0.2 over 24.2 plus 0.08. So the 0.08 is simply delta I over I. In fact, delta I over I is equal to 8%, and 8% is simply 0.08. And this is how we got the 0.08. So if we calculate, we will get delta R over R equals to 0.08826. Then we make delta R subject and obtain delta R equals to 0.08826 times R, which is equal to 0.08826 times V over I. We have the values of V and I, and therefore we have 0.08826 times 24.2 divided by 2.5, and this result is in ohm. And we obtain delta R as delta R equals to 0.8544 ohm, which is returned to one significant figure as delta R equals to 0.9 ohm. Once we got the delta R, so we have the value of our resistance as 9.68 plus or minus 0.9 ohm. And if we match the number of decimal places, meaning we write the value 9.68 to one decimal place to make it the same number of decimal place as the uncertainty, then we will have R equals to 9.7 plus or minus 0.9 ohm.